Welcome to our cosmic journey through the universe of stars. When you look up at the night sky, you see a twinkling tapestry of light. Each point of light represents a distant sun, some similar to our own, others vastly different. Today we'll explore the fascinating types of stars that light up our night sky, from the familiar glow of main sequence stars to the enigmatic presence of black holes. Prepare to be amazed by the sheer diversity and wonder of these celestial objects. Let's start with the type of star our own sun is, a main sequence star. These stars are the most common in the universe and represent a star in the prime of its life. They're like the cosmic adults, responsibly fusing hydrogen into helium in their cores. This process releases enormous amounts of energy, making them shine brightly. Our sun, a yellow dwarf star, has been on the main sequence for about 4.6 billion years and has billions more to go. Main sequence stars come in a range of sizes and temperatures, from cool reddish stars to hot bluish white ones. More massive stars are hotter, brighter, and burn through their fuel much faster, like a cosmic SUV compared to a fuel-efficient compact car. Eventually they exhaust the hydrogen in their core, setting the stage for their next act in the cosmic drama. When a main sequence star like our sun runs low on hydrogen fuel, it doesn't simply fade away. Instead, it enters a new phase of existence, expanding dramatically to become a giant star. Imagine a balloon inflating, its surface stretching thinner and cooling down even as it takes up more space. As the core contracts and heats up, the outer layers of the star expand outward, engulfing any inner planets in the process. In our own solar system, the sun will eventually expand to become a red giant, engulfing Mercury, Venus, and possibly even Earth. Giant stars are cooler than their main sequence counterparts, giving them a reddish or orange hue. But what they lack in temperature, they make up for in size and luminosity. They can be hundreds of times larger and thousands of times brighter than our sun. Now, if giant stars are impressive, supergiant stars are truly awe-inspiring. These are the cosmic titans, the largest and most luminous stars in the universe. Imagine a star so large that if it were placed where our sun sits, its surface would extend beyond the orbit of Jupiter or even Saturn. Supergiants are like the rock stars of the cosmos, living fast and dying young. They burn through their fuel at an extraordinary rate, making them incredibly bright, but also incredibly short-lived. One of the most famous supergiants is Rigel, a blue supergiant in the constellation Orion. Eventually, it will exhaust its fuel and explode as a spectacular supernova, scattering its enriched guts across the cosmos. While supergiants grab the headlines with their size and brilliance, dwarf stars are the cosmic underdogs, small but mighty. Don't let their name fool you. These stars are incredibly common, making up the vast majority of stars in the universe, including our own sun. Dwarf stars come in a variety of flavors, from red dwarfs, the smallest and coolest, to white dwarfs, the remnants of stars like our sun. Red dwarfs, for example, can live for trillions of years, far longer than the current age of the universe. White dwarfs, on the other hand, are the remnants of stars that have exhausted their nuclear fuel. They're incredibly dense, packing the mass of the sun into a sphere roughly the size of Earth. White dwarfs no longer produce energy through nuclear fusion. Instead, they slowly cool down over billions of years, eventually fading away into obscurity as black dwarfs. If white dwarfs are dense, neutron stars are downright mind-boggling. Imagine taking an object with the mass of the sun and squeezing it down to the size of a city, say Manhattan. These extreme objects are born from the death throes of massive stars, those at least 8 times more massive than our sun. When these stars run out of fuel, their cores collapse under their own gravity, triggering a supernova explosion that can outshine an entire galaxy. The core, however, survives this cosmic cataclysm, compressed to unimaginable densities. At these densities, protons and electrons are forced to combine, forming a sea of neutrons. Neutron stars are like giant atomic nuclei held together by gravity. They spin incredibly fast, some rotating hundreds of times per second due to the conservation of angular momentum. This rapid rotation, combined with their intense magnetic fields, can create beams of radiation that sweep across the cosmos like cosmic lighthouses. If neutron stars represent the extreme limit of matter, then black holes represent the extreme limit of gravity. These enigmatic objects are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. Black holes form when massive stars, much larger than those that form neutron stars, collapse at the end of their lives. As the core collapses, its gravity warps space-time so severely that it creates a singularity, a point of infinite density and zero volume. Surrounding this singularity is the event horizon, the point of no return. Once you cross the event horizon, there's no coming back, not even for light itself. Black holes are invisible to telescopes that detect light, X-rays, or other forms of electromagnetic radiation. However, we can infer their presence by the way they interact with their surroundings. Not all stars shine with a constant light. Variable stars, as their name suggests, change in brightness over time. These changes can occur over periods of hours, days, or even years, and they provide astronomers with valuable clues about the star's internal workings. There are two main types of variable stars, intrinsic and extrinsic variables. Intrinsic variables change in brightness due to physical changes within the star itself, while extrinsic variables change in brightness due to external factors, like an eclipsing companion star. One of the most famous types of intrinsic variable stars is the Cepheid variable. These stars pulsate radially, expanding and contracting like beating hearts, causing periodic changes in their luminosity. This period-luminosity relationship makes Cepheid variables incredibly valuable tools for measuring cosmic distances. Before a star becomes a shining beacon of light, it begins its life as a protostar, a stellar embryo nestled within a vast cloud of gas and dust called a nebula. These nebulae are like cosmic nurseries where the raw materials for stars are gathered and nurtured. The formation of a protostar begins when a region within a nebula, perhaps disturbed by a passing shockwave from a supernova explosion, becomes denser than its surroundings. This denser region exerts a stronger gravitational pull, drawing in more gas and dust from its surroundings. As the cloud collapses, it heats up due to the conservation of energy, much like a bicycle pump gets warm when you compress the air inside. The core of the collapsing cloud becomes increasingly hot and dense, eventually reaching temperatures of millions of degrees. At these temperatures, the core of the protostar begins to glow, emitting infrared radiation that can be detected by telescopes here on Earth. Eventually, the core of the protostar becomes hot and dense enough to ignite nuclear fusion, the process that powers stars. If supergiants are the rock stars of the cosmos, then Wolf-Rayet stars are the wild ones, the rebels with a cause, living fast, burning bright, and leaving a trail of stellar chaos in their wake. Named after French astronomers Charles Wolf and Georges Rayet, who first discovered them in the 19th century, Wolf-Rayet stars are incredibly rare, with only a few hundred known in our entire Milky Way galaxy. What makes them so unique is their extreme temperatures and intense stellar winds. These stars are incredibly hot, with surface temperatures exceeding 50,000 degrees Celsius, making them some of the hottest stars known. Their intense radiation pressure drives powerful stellar winds, expelling material from their outer layers at millions of kilometers per hour. These stellar winds are so powerful that they can strip away a star's outer layers, revealing its hot, helium-rich core. This gives Wolf-Rayet stars their characteristic spectra, with broad emission lines indicating the presence of heavy elements like carbon, nitrogen, and oxygen. Wolf-Rayet stars are thought to be the descendants of massive stars that have lost a significant fraction of their mass through stellar winds. Just as human children go through a period of growth and development before reaching adulthood, so too do young stars. T Tauri stars, named after the prototype star T Tauri in the constellation Taurus, are stellar toddlers still in the process of gravitational contraction. These stars are relatively young, typically less than 10 million years old, and are still accreting material from the surrounding disk of gas and dust that gave birth to them. This accretion process can be messy and chaotic, leading to dramatic fluctuations in the star's brightness. T Tauri stars are often surrounded by protoplanetary disks, the birthplaces of planets. These disks are composed of gas and dust that is gradually coalescing to form planets, asteroids, and other celestial bodies. Studying T Tauri stars and their protoplanetary disks provides astronomers with valuable insights into the processes that led to the formation of our own solar system. T Tauri stars represent the transition from a collapsing cloud of gas and dust to a fully formed main sequence star. Thanks for joining us on this stellar journey. We've explored the incredible diversity of stars, from the familiar glow of main sequence stars to the enigmatic presence of black holes. Each type of star tells a unique story, a chapter in the grand narrative of cosmic evolution. Don't forget to like, subscribe, and hit the bell icon for more cosmic content. Keep looking up and stay curious.